Welcome back, everyone. Today, we're going deep on something I think a lot of you grad students out there are going to find pretty fascinating.
Oh, yeah.
Yeah, photocatalysis,
Okay. Yeah, that's a big one. Definitely hearing that name a lot these days.
for sure. And I mean, who doesn't love the idea of using light to power chemical reactions, right?
It's pretty elegant when you think about it.
Totally.
Yeah.
So for this deep dive, I've got a lecture presentation from university course that does a pretty good job of breaking it all down.
Awesome. Looking forward to hearing what they have to say.
Yeah. So I guess to kick things off, maybe you could give us the official definition of photocatalysis. How would you explain it to someone who's maybe hearing about it for the first time?
Okay, so at its core, photocatalysis is basically using light to accelerate a chemical reaction. And the key player here is the photocatalyst, which is a material that can absorb light and use that energy to kind of kickstart the reaction.
So it's like a catalyst, but instead of heat or pressure or something, it's using light as the energy source.
Cool.
That's pretty cool. So the photocatalyst itself doesn't get used up in the reaction. It just helps things along.
Exactly. It's like a facilitator, just helping the reaction happen faster.
Gotcha. So where did this whole idea come from? Is it a fairly recent thing or does it have a longer history?
Actually, it's got a pretty interesting history. Way back in the early 1900s, there was this Italian chemist named Giacomo Siamission,
Right.
and he had this vision of using light and light alone for chemistry.
Wow. So he was way ahead of his time.
Oh, absolutely. But like a lot of visionary ideas, it took a while for the technology to catch up.
Right. So when did things really start to take off?
Well, it wasn't until the 1970s that things really got moving. There was this groundbreaking discovery by Fukushima and Honda.
Oh, yeah.
They showed that you could actually produce hydrogen from water using titanium dioxide as a photocatalyst.
Whoa. So that was kind of a turning point, a real aha moment.
Yeah, definitely. It was a proof of concept that got everyone really excited about the possibilities.
That makes sense. Okay, so we've got light, we've got a photocatalyst, and we've got a reaction that gets sped up. But before we get too deep into the how of it all, I think it's worth taking a second to appreciate just how much energy is packed into sunlight. Right? I mean, we hear it all the time, but it's kind of mind-blowing.
Oh, totally. It's
Mhm.
it's pretty crazy when you think about it.
Yeah, do you have any stats or figures that really illustrate that?
Yeah, for sure. So get this. 1 hour of sunlight hitting the Earth contains more energy than the entire planet uses in a year.
No way.
Yeah, just let that sink in for a second.
That's wild. No wonder everyone's so
Oh.
keen on harnessing it.
Right.
Okay, so we've got this incredible energy source. Now let's dive into the how. I remember back in undergrad struggling with band theory.
Yeah.
How does all that play into photocatalysis? Can you give us a quick refresher?
Okay, yeah, band theory. So basically, the idea is that electrons in solid materials can only exist at specific energy levels. And these levels, they kind of group together to form these things called bands. And the highest energy band that's full of electrons is called the valence band.
Gotcha.
And then the next one up, which is usually empty, that's called the conduction band.
Okay, so it's like electrons have their assigned spots in the valence band, but they can jump up to the conduction band if they get enough energy.
Exactly. And the energy difference between those two bands, that's called the band gap.
So it's like the minimum energy an electron needs to make that jump.
Precisely.
Cool. So how does that relate to conductors, insulators, and all that?
All right, so conductors, they have essentially zero band gap, so electrons are free to move around, no problem.
Okay.
Insulators, on the other hand, have a huge band gap, so those electrons are basically stuck.
Stuck in the valence band.
Yeah, exactly. But then we have semiconductors, and they have a band gap that's, not too big, not too small.
Like the Goldilocks of materials.
Uh-huh. Yeah, exactly.
So they're kind of the sweet spot for photocatalysis
Mhm.
because their electrons can be excited by light, but aren't just running around freely all the time.
You got it.
Makes sense.
Now, there's actually different types of band gaps, too, direct and indirect, which affect how easily those electrons transition.
Oh, interesting. So in a direct band gap, the electron just jumps straight up to the conduction band.
Yeah, it's a straight shot.
But in an indirect band gap, it needs a little help.
Yeah, it needs a change in momentum, too. It's a little more complicated.
So direct band gap is more efficient because it's like a straight shot for the electron.
Exactly. And, this is where the material science gets really interesting because
Okay.
even the same material, like molybdenum disulfide, can have a different band gap type depending on how it's structured. So a single layer of molybdenum disulfide that's got a direct band gap. But when
Mhm.
you have multiple layers, it becomes indirect.
Wow. So the way you put the material together actually affects its electronic properties.
Yeah.
That's something to keep in mind when designing new photocatalysts, right?
Absolutely. It's all about optimizing the material for maximum efficiency.
Okay, this is starting to come together.
Oh.
So we've got our semiconductor. It's at that just right band gap, and we shine some light on it. What happens next?
All right, well, that's where the real magic starts to happen. Let's break down the mechanism of photocatalysis step by step, shall we?
Okay, I'm ready.
Okay, so picture this right. A photon of light comes along, hits our semiconductor, and if it has enough energy, boom. An electron in that valence band, it absorbs that energy and jumps up to the conduction band.
It's like gets a boost to reach that higher level.
Exactly. And now here's the thing. When that electron moves up, it leaves behind kind of a vacancy,
Okay.
in the valence band, and we call that a hole, and it acts like a positive charge.
So now we've got the separation of charges happening inside the material.
Right, and this is where things get really interesting. That excited electron up in the conduction band and that hole down in the valence band, they've got a couple of options now. Yeah, so they can either recombine, which is kind of a bummer because they just cancel each other out.
Yeah.
Or, and this is what we're hoping for, they can migrate to the surface of the semiconductor and react with whatever molecules are hanging out there.
Gotcha. So it's like a race against time. If they recombine, nothing really happens. But if they reach the surface, they can trigger chemical reactions.
You got it. And that's how we can drive these redox reactions, reduction and oxidation. The electron can reduce something and the hole can oxidize something. You're essentially getting like 2 reactions for the price of 1 photon.
That's pretty awesome. That's like a tiny light-powered chemical factory.
Mm.
But I imagine it's not quite as simple as, like, just shining any old light on a semiconductor, right? I mean, there must be a whole bunch of factors that influence how well this process works.
Oh, for sure. There are tons of parameters that come into play when you're talking about photocatalysis.
Like what kind of things?
Well, for starters, how much catalyst you're using makes a big difference.
Okay, so the mass of the catalyst, I guess that makes sense, right?
Yeah.
More catalyst means more active sites where those reactions can happen.
Yeah, that's the general idea. But it's not quite that straightforward.
Oh.
Yeah. You see, there's this thing called optimal catalyst loading. So initially, increasing the catalyst mass, it does lead to a faster reaction rate.
Okay.
But there's a limit. At some point, adding more catalyst doesn't really do anything because you've already got all the particles fully illuminated.
Ah, I see. It's like if you have a room full of people and you keep adding more lamps, eventually it doesn't get any brighter because everyone's already in the light.
Exactly. So it's all about finding that sweet spot where you're using enough catalyst to get the job done, but not wasting any.
Makes sense. So what about the light itself? Does the wavelength matter?
Oh, absolutely. Remember, the photocatalyst needs to absorb that light energy to kick those electrons up to the conduction band. So the wavelength of the light has to match the absorption spectrum of your photocatalyst. If the energy of the light isn't high enough, the electron won't be able to make that jump.
So it's like you need the right key to fit the lock.
Exactly. So choosing the right light source for your specific photocatalyst, that's super important.
What about the concentration of the reactants? Does that come into play?
Yeah, definitely. The relationship between the concentration of your reactants and the rate of the reaction, it often follows what's called the Langmuir-Hinge-Shellwood mechanism.
Okay, and what's that?
So basically, at low concentrations, if you increase the amount of reactant, you'll speed up the reaction. Makes sense, right?
Yeah.
But then at a certain point, you hit this plateau where adding more reactant doesn't really do anything anymore.
Interesting. So there's like a sweet spot where you have enough reactant to keep things moving, but not so much that it gets crowded.
Exactly. It's all about balance.
Makes sense. Now, what about temperature? I mean, does temperature play a role in photocatalysis?
Yeah, temperature is always a factor in chemistry, right?
Right. But the interesting thing about photocatalysis is that it's often less temperature dependent than other types of reaction.
yeah.
Yeah, and sometimes higher temperatures can actually be a bad thing.
How so?
Well, higher temperatures can increase the rate of that electron-hole recombination we were talking about.
Oh, right. Because we want those charges to stay separated so they can do their thing at the surface.
Exactly. So, again, it's all about finding that optimal temperature range where you're maximizing the efficiency of the process.
So it's not just a matter of cranking up the heat and hoping for the best.
Nope. Photocatalysis is a bit more nuanced than that.
Okay, cool. What about pH? Does that play a role too?
Oh, yeah. pH is definitely a big one, especially for reactions happening in water. Which, I mean, that's going to be relevant for a lot of research, right?
Absolutely. So the pH of the solution can affect the surface charge of the photocatalyst, and that can influence how it interacts with the reactants and how efficient the whole process is. Some reactions might work best under acidic conditions, while others might do better in a basic environment.
So it's another parameter to optimize for each specific reaction.
Exactly. It's all about fine-tuning those conditions to get the best results.
Okay, so we've talked a lot about the potential of photocatalysis, but I think it's also important to be realistic about its limitations, right? I mean, nothing's perfect.
Oh, absolutely. Photocatalysis is a super exciting field, but it definitely has its challenges.
Like what? What are some of the things that researchers are still trying to figure out?
Well, one of the big ones is that a lot of photocatalysts, they're really good at absorbing UV light,
Okay.
but not so much visible light.
And I mean, visible light is a huge part of the solar spectrum.
Right. So if we could figure out how to make photocatalysts that are more efficient at absorbing visible light, that would be a major breakthrough.
So it goes back to that matching the light source to the photocatalyst thing.
Exactly. If it can't absorb the light, it can't use the energy.
Makes sense. What other challenges come to mind?
Another big one is electron-hole recombination. Remember how we talked about how those charges need to stay separated and make it to the surface?
Yeah.
Well, a lot of times they recombine really quickly, which kind of throws a wrench in the whole process.
So it's like they're constantly trying to get back together and we're trying to keep them apart.
Exactly. And then that brings us to another limitation, low quantum efficiency, which is basically a measure of how many photons actually lead to successful chemical reactions.
So even if we get those electrons and holes to the surface, they don't always lead to a reaction.
Right. And in a lot of cases, this quantum efficiency is still pretty low, which means we're not really making the most of that light energy.
Okay, so we're capturing the light, but we're not necessarily converting it into useful chemical reactions as efficiently as we'd like.
Exactly. There's definitely room for improvement there.
Makes sense. Are there any other limitations that come to mind, especially when you think about moving beyond the lab and into real-world applications?
Yeah, definitely. I mean, scaling up these processes and making them economically viable, that's a big challenge.
Right, it's one thing to get amazing results in a small-scale experiment, but it's a whole other ballgame when you try to do it on an industrial level.
Exactly. So those are some of the hurdles that researchers are still working on overcoming.
Okay, so there's still a lot of work to be done, but it sounds like there's also a lot of potential.
Oh, absolutely. Photocatalysis is still a relatively young field, and there's so much more to explore.
So knowing all this, what makes a good photocatalyst? What are the kind of things that researchers are looking for when they're designing these materials?
That's a great question. There are a few key properties that really make a photocatalyst stand out from the crowd. So first off, the band gap, it's got to be just right. Like Goldilocks.
Not too big, not too small.
Exactly. Large enough to provide enough energy to drive those reactions, but not so large that it can't absorb a good chunk of the solar spectrum. Got to find that sweet spot.
Right, right. What else? What else is important?
Well, efficient charge transfer is super important. You want those excited electrons and holes to separate quickly and stay separated long enough to reach the surface and do their thing.
So they can react with those molecules that are hanging out there.
Exactly. If they recombine too quickly, poof, the process loses efficiency.
So it's a race against time for those charge carriers.
Got it.
Okay, what about surface area? I feel like that's got to play a role too, right?
Oh, absolutely. Generally speaking, a higher surface area means more active sites where those reactions can happen.
More space for those reactions to take place.
Right. Think of it like if you have a bigger dance floor, you can fit more dancers. Right?
Yeah, that makes sense. So we're maximizing the real estate for those chemical reactions.
Exactly.
Okay, cool. Now what about stability? How long do these photocatalysts need to last to be useful in the real world?
Yeah. Stability is key, for sure. Ideally, we want photocatalysts that can hang in there for a long time,
Right.
withstand all that exposure to light, chemicals, whatever the environment throws at them, without breaking down.
So durability is a big factor.
Oh, yeah, for sure. I mean, if it falls apart after a couple of uses, it's not going to be very practical, right?
Makes sense. So considering all these factors, are there any, star players in the photocatalyst world?
Yeah.
Any materials that really stand out?
Yeah, there are a few metal oxides, like titanium dioxide. Those are some of the most popular.
Titanium dioxide, that's the stuff in sunscreen, right?
Exactly.
So it's already out there doing good work.
For sure. And they're relatively stable, inexpensive, and they've been studied a ton.
Right, right. So what else is out there? Are there other promising materials?
Oh, yeah, tons. Metal sulfides are interesting. They often have narrower band gaps so they can absorb visible light more efficiently.
Oh, so that helps with that whole capturing more of the solar spectrum thing.
Yep. And then you've got ternary compounds like titanates and tungstates. Those have some pretty unique electronic properties.
Okay, so we're not limited to just those basic metal oxides.
Nope. And then there's non-metal semiconductors like graphitic carbon nitride. Those are showing a lot of promise, especially for organic synthesis.
Wow, it's like a whole periodic table of possibilities.
Pretty much. It's a really exciting time to be working in this field.
Yeah, for sure. So how do researchers actually go about designing and improving these photocatalysts? What are some of the strategies they're using?
Oh, they're getting super creative. One approach is to play around with the morphology of the photocatalyst, so that's its size and shape.
Okay.
So like making smaller particles can increase the surface area, but it can also decrease light absorption. So
Yeah.
got to find that balance.
Right, so it's a trade-off. You want more active sites, but you also need to make sure you're capturing enough light.
Exactly.
What about different shapes? Does that make a difference?
Oh, yeah, the shape can influence how light scatters within the material, how well those charges separate, even how exposed the active sites are. It's like designing a building to maximize sunlight or airflow.
So it's not just what it's made of, but how it's put together.
Precisely.
So what other tricks do researchers have up their sleeves?
Well, another really cool area is creating these things called heterostructures.
Okay, what are those?
So that's basically combining different materials to create a super efficient photocatalyst.
So like a hybrid material.
Yeah, exactly.
Yeah.
So you could combine a material that's really good at absorbing light with another one that's great at separating charges, for example.
So you get the best of both worlds.
Exactly.
That's pretty clever. What are some other ways to enhance those photocatalytic properties?
Well, adding metal nanoparticles is another common strategy.
Like what kind of metals?
Platinum, gold, palladium, those kinds of things.
Okay.
And they can act as electron sinks, so they basically trap those excited electrons and prevent them from recombining with the holes.
So they're helping to keep those charges separated.
Yep. And they can also enhance the catalytic activity of the material itself.
So they're like little helpers, making the whole process run more smoothly.
You got it.
Are there any other modification techniques that are being used?
Oh, yeah. Doping is another one.
Doping.
Yeah, that sounds kind of weird, but it's basically intentionally introducing impurities into the photocatalyst.
Okay.
And that can actually modify its band gap or create these little traps for those charge carriers, which can actually improve its performance.
So it's like fine-tuning the electronic properties of the material.
Exactly.
Wow, it's amazing how much control we have over these materials at the nanoscale. But with all these different modifications and materials, how do researchers actually study these photocatalysts? How do they figure out what's going on at the atomic level?
Well, they use a whole bunch of different techniques. UV-vis spectroscopy, that's a big one.
Okay, and what does that tell them?
So that basically measures how much light the material absorbs at different wavelengths, which can help them figure out the band gap energy and understand its light absorption capabilities.
So it's like shining light on the material and seeing how much gets through.
Pretty much. And then there's photoluminescence spectroscopy. That's another important one.
Okay.
That measures the light that's emitted from the material after it absorbs photons. So that can give you insights into the behavior of those excited electrons and holes.
So they're basically watching those charge carriers in action.
Exactly. And then you've got those really high-tech synchrotron techniques. Those can provide some incredible insights.
Yeah, we touched on those earlier. What kind of information do those give you?
So ambient pressure X-ray photoelectron spectroscopy, or APXPS for short, that allows researchers to study the actual photocatalytic reactions as they're happening in real time under controlled conditions. And then X-ray photoemission electron microscopy, or XPEM, that can give you these incredibly detailed images of the surface of the photocatalyst at the nanoscale.
So we're talking about seeing things at a ridiculously small scale.
Oh, yeah, the resolution is incredible.
That's amazing. But I guess it's all in service of a good cause, right? We started this whole conversation talking about some of the amazing potential applications of photocatalysis.
Yeah.
Are we actually starting to see those applications become a reality? Or is it still mostly in the research phase?
No, it's definitely moving beyond the lab. We're seeing pilot plants for hydrogen production using photocatalysis.
Wow.
Yeah, and some water purification systems are starting to incorporate these photocatalytic materials to break down contaminants.
So the technology is starting to make a real-world impact.
Absolutely. It's really exciting to see.
Yeah, for sure. What about those other applications we talked about, like using photocatalysis for clean energy or in medicine? What's the future looking like for those areas?
I think the sky's the limit. For clean energy, I mean, imagine producing hydrogen fuel from water using sunlight. That would be a game changer. And in medicine, there's potential for targeted cancer therapies and antibacterial applications. I mean, the possibilities are huge.
It really is incredible to think about. It sounds like photocatalysis could be a real game changer in so many different fields.
Oh, for sure.
So what are some of the big questions that researchers are still trying to answer? What are the next frontiers in this field?
Well, one of the big challenges is figuring out how to make photocatalysis more efficient and cost effective on a large scale, so it can really compete with traditional methods.
Right.
So researchers are working on designing better photocatalysts, optimizing those reaction conditions, and just coming up with new and innovative ways to harness the power of sunlight.
So there's still work to be done, but it sounds like we're on the right track.
Absolutely. It's a dynamic and rapidly evolving field. It's a really exciting time to be involved in photocatalysis research.
Well, that's a great note to end on. I gotta say, I'm feeling pretty inspired after this deep dive. It's amazing to see how these fundamental principles of chemistry and material science can be applied to tackle some of the biggest challenges facing our world. And for all you grad students listening out there, I mean, this is a field that's ripe with opportunities for innovation and discovery.
Couldn't agree more.
If you're looking for a research area with real-world impact, photocatalysis might just be your calling. So thanks for joining us on this journey into the world of photocatalysis. Until next time, keep exploring, keep asking those questions, and keep pushing the boundaries of science.
Cheers to that.